Welcome back. Let's have a recapture of the things we discussed so far because you are preparing for a quiz on Friday. Yes. So, let's begin with when you have two chords that intersect inside of a circle. And I remember last year I would use the concept piece times piece. So for one chord, let's say chord 1, you will multiply piece of it times the other piece. So piece times piece for one chord equal piece times piece for the second chord. So once again, looking at the first chord, I will multiply this piece A times this piece B and set that product equal to, for the second chord, C times D, piece times piece. And then when you have two secants that meet at a point on the outside, all right, for the secant, you want to multiply the outside times the measure of the whole secant segment. So focusing on this first secant here, segment here, we have the outside part, A, times the measure of the whole thing. To get the measure of the whole thing, we add the outside part plus the inside. So that would be A plus B. And set that product equal to, for the other secant segment, we would take the outside part, C, and multiply that times the measure of the whole thing. And to get the measure of the whole thing, we add the outside, C, plus the inside, D. Okay? And then last but not least, you may have a secant and a tangent that meet at a common point on the outside. So for the secant segment, well, I like to begin with a tangent. You would take the measure for the tangent, C, and square it. And set that equal to, focusing on the secant segment, you take the outside part, A, and multiply that times the measure of the whole secant segment. To get the measure for this whole secant segment, we add the outside part, A, plus the inside, B. And you have your equations. Likewise, we have some other properties we would like for you guys to use or apply on the quiz tomorrow. And we're going to focus on the segment lengths using properties of tangents. All right, so we need to prove this theorem before we can apply it in class, so let's do it together. Begin with the measure of angle PSO and the measure of angle PTO. This angle and this angle, they each have a measure of 90 degrees. And we're going to just accept that this was given to us, okay? Likewise, it tells us for step 2 that the measure of segment SO is equal to the measure of segment TO. So let's place some tick marks here. How do we justify that they're equal? All radii of a circle, they use the symbol for circle, are congruent. Let's move to statement 3, and now we need to justify that segment PO is congruent to segment PO. Why is this? Because this segment serves as a side for both triangles. How do we justify that segment PO is congruent to itself? This is by the reflexive property of congruency. If segment PO is congruent to segment PO, then we can show that the measure of segment PO is equal to the measure of segment PO. And this is by the definition of congruency. So at step 5, we can now show that, and this should be that triangle PSO is congruent to triangle PTO. We can now justify that these two triangles are congruent. But by which reason do we use? First of all, we recognize that these are both right triangles. And we can recognize that their hypotenuses are congruent, the side they share. And likewise, they have a pair of corresponding legs that are congruent. So therefore, they are congruent by the hypotenuse-leg congruency theorem. And if that's the case, now we can prove that segment SP, from point S to point P, is congruent to segment TP, from point T to point P. If you notice, segment SP and segment TP are both tangent segments. They're both tangent segments to that circle. So we are now proving that anytime you have two tangents to a circle, once again, anytime you have two tangents to a circle and they meet at a common point outside the circle, then those two segments are congruent, but only from that common point to the point of tangency. So from point P to point T is the same measure as going from point P to point S. And this is by CPCTC. So now that we have proven this theorem, we can apply it anytime we need to use it. Okay, so let's complete this. Tangent segments. Once again, tangent segments from a common external point are They're always congruent. So we're going to skip around the sheet and look at a few problems that are applying this concept and use it a few times so you guys get used to it. And when you see anything like this on your quiz tomorrow, then you know how to set up your equations. Let's begin with problem number 5 at the bottom. It asks you to find the value of x. Notice that segment RS is a tangent to the circle. Likewise, segment RT is a tangent to the circle. And they both share a common point, external point outside the circle. Therefore, from point R to point S, from point R to that point of tangency S, is the same measure as going from point R to the other point of tangency for that circle, point T. Alright, so if these two segments are congruent, then we can set their measures equal. So to set up this equation, you would say that 2 times x plus 4 has the same measure as 26. So let's solve it. And of course, we'll move forward to the other side with this like term. And that leaves 2 times x is on the left equal to 22. Divided side by 2, we find that x is 11. And to check our work, to make sure that it makes sense, we will go back and place this measure into the expression for x. 2 times 11 is 22, and 22 plus 4 is 26. So this segment RT has the same measure as segment RS. Okay, so let's flip our worksheets to the other side and look at some other problems that involve the same concept. Let's look at problems 4 through 6. We can see that we have circles, and for those circles we see tangents to the circle. And these two tangents have a common external point. Therefore, we can show that the two tangents involved have the same exact measure. So segment KJ has the same measure as segment MJ. So we can place congruency markers, tick marks, and then set up our equation. So 4 times x plus 7, the measure for this tangent, is equal to the measure for this tangent. You have your equation, you set it up, and you solve it. Alright, so I'll move 4x first, and that leaves 7 is equal to 3x minus 8, then add 8 to both sides, and that leaves 15 is equal to 3 times x. Divided side by 3, x has a value of 5. So why don't you try problem 5? Well, for time's sake, let's go ahead and do 5 together. But you go ahead and get started. I'll catch up with you. We have 3 times x squared minus 10. We set that expression equal to 17. Once again, because we have two tangents to a circle. This is the point of tangency, this is the point of tangency. So from the external point to the point of tangency here, it's the same measure going from the external point to the point of tangency. So now let's solve this. I would add 10 to both sides of the equation. That leaves 3 times x squared equal to 27. Divide each side by 3. That leaves x squared is equal to 9. Take the square root of both sides. X is 3. And we're through. And you would do the same for problem 6. You would set these two measures equal and solve for x. So I'll let you complete this tonight. Okay? Let's move on to a new concept. What else do they want us to learn from this worksheet? Well, let's look at examples 1 through 3. Beginning with example 1. And once again, I move back to the front of the worksheet. That's another concept that we need to apply when we're taking the end of course test. Alright, so we see that segment ST, it is tangent to the circle, because point S is a point of tangency, to circle Q. Find the value of R. One thing that we haven't discussed, but you need to know, anytime you have a radius, this is a radius, and you have a tangent, and the radius and the tangent meet at the point of tangency. Once again, if you have a radius, and the radius meet the tangent line at the point of tangency, when they intersect, they will always be perpendicular to each other. And if they are, we have a right triangle. You see the same concept here. You see a tangent to the circle. But look, this tangent, this point of tangency is also an endpoint for a radius of that circle. When that radius and that tangent line meet at that point of tangency, they are perpendicular. Likewise up here, you have another tangent. That tangent, that point of tangency is also an endpoint of the radius. So when they meet, they are perpendicular. You see a right angle. And the same thing here. You have a tangent, and that point of tangency is also an endpoint for a radius. And anytime you see this happens on a standardized test, you know you have a right angle involved, or a right triangle. So, they want us to solve for R. Think about relationships. How do we form an equation when we have something like this? Well, we're looking at all three sides of a right triangle. So we want to use Pythagorean theorem. What is Pythagorean theorem? A squared plus b squared is equal to c squared. I'll do several problems like this with you so you guys can have something to look at, go home, rework them, and then try some of your own.